All right, let's start again. We'll recap what we've already done. We're measuring a compound that contains only aluminum, carbon, and hydrogen. From the CO2 amount that was generated, we determined there was 0.154757 grams of carbon and 0.032477907 grams of hydrogen. By adding these two amounts and subtracting from the total weight of the compound, we get the mass of the aluminum, which is 0.0579651 grams of aluminum. Now that we have the individual amounts, we can find their molar amounts so that we compare whole number molar ratios. So if we start with carbon, 0.15475 grams of carbon divided by the molar mass, 12.011 grams of carbon, yields 0.012885678 moles of carbon, and then 0.032477907 grams of hydrogen divided by the molar mass of hydrogen, which is 1.0078 grams of hydrogen, gives us the number of moles of hydrogen, which is 0.032226539 moles of hydrogen. And then finally, the aluminum, 0.0579651 grams of aluminum divided by the molar mass, 26.981 grams of aluminum, gives us 0.002147897 moles of aluminum. Now, in determining the molar ratios, the whole number molar ratios, we want to use the smallest existing number of moles, divide that by itself, and then divide the other two components in this compound by that smaller number of moles, which in this case belong to aluminum. So we do that, and we come up with a molar ratio of 6 moles of carbon, 15 moles of hydrogen, and 1 mole of aluminum. And that makes sense because when we're dividing by the smallest, which is the number of moles of aluminum, which also makes sense because aluminum has the highest molar mass and the smallest amount of, well, among the smallest amounts of grams of substance. So this big number into a small number is going to give us an even smaller number, and giving that smaller number into itself gives us 1, into the much larger number of hydrogens gives us 15, and then dividing that into the number of moles of carbon gives us 6. So we have aluminum C6H15, which I happen to know is aluminum triethyl chloride, or aluminum triethyl excuse me. I'll say that 4 times fast. So C6H15 is just like C2H53. And you would find that out not from the elemental analysis that we did, but from a mass spec. Okay, so thank you. That covers that problem, problem 12 on the practice test. If you have any questions, be sure to hit me up. Greetings. Here's problem 2.84 from homework 2. It's a simple naming problem. If you'll notice, we have sodium and nitrogen. And whenever we name compounds, we'll talk about the metal first. So just so happens sodium is in blue. And so if we're naming that, we're going to call it the name of the metal in lowercase letters. And then we're going to take the non-metal, nitrogen, and change the ending from gen to ide. So nitride. Okay, sodium nitride. And that would be, now, this is a little bit harder. You want to do the symbols. Sodium is a +1. Nitrogen, or nitride, which is the anion of nitrogen, is an N3 minus. So in order to balance that charge, we're going to need 3 sodium pluses to make a negative charge of 3 to balance that compound, and we're going to get Na3N. Okay. Let's look at the next one, part B, right? We have oxygen and strontium. And fortunately for me, the non-metal is in black, and then the metal is in blue. Strontium is the metal. It's in the second column, an alkaline earth metal, right here, number 38. Okay, so metals come first. Strontium is a 2+, right? So if we're doing the symbol, strontium 2+, and oxygen is 2-, right? So they balance. So the symbology would be, the chemical symbol would be, for the compound, would be SrO. And then if we're naming it, the metal comes first. So strontium, again, with lowercase letters saying the name of the metal, and then oxygen comes next, and we change the ending from gen to ide. So ox, and I did both times now. I've done that. Oxide. So from oxygen to oxide. Finally, the third one would be aluminum and chlorine. Again, the metal comes first, so aluminum. And then the nonmetal chloride. Chlorine is changed to chloride. I do it automatically because I've done it so many times. Aluminum chloride. Now, when we put together the symbols, aluminum is a 3+, chlorine is a 1- anion. So in order to balance that out, we need 3 chlorines to make 3-, because 3- plus 3+ equals 0, or charge balance. So we need aluminum chloride. And while that may not be part of the assignment, we did both parts, right? Naming and the symbols. So let's look again. Sodium and nitrogen. Sodium's the metal. Nitrogen's the non-metal. So we say the name of the metal and change nitrogen to nitride. Sodium's a 1+. You need 3 of those to balance out the negative charge of the nitride. Na3N. Oxygen and strontium. Strontium is a 2+ metal. Oxygen is a 2- non-metal. So when we write it, the metal comes first, SrO, because it's a 1-to-1 ratio. Then we say the name of the metal, strontium. Change the name of the non-metal from oxygen to oxide, so strontium oxide. And finally, aluminum and chlorine. We say the name of the metal, aluminum. Change the name of the non-metal from chlorine to chloride, IDE, and aluminum chloride. Aluminum is a 3+ metal, always in this class, and then chlorine is a 1- metal because it's halogen, and all the halogens are -1 anions. So 3 of those plus a 3+ equals 0 to charge balance, and we get aluminum chloride. And you don't have to say aluminum 3-chloride. All right, that's it. Greetings. Look at problem 2.88 on the homework. We want to give a formula or a name based on what's given to us. So in problem A, we have tin 4-chloride. Tin is the metal. Tin symbol is Sn. It's going to be a 4+ given the Roman numeral, which tells us the charge. Not how many, just the charge. And then chloride is Cl minus, the anion. So we have a 4+. In order to charge balance, we need a 4-, so we have to give 4 chloride anions. So if we're going to write this as a symbol or the formula, SnCl4, okay? Tin 4-chloride. Let's look at the next one. We have iron. Iron is a transition metal. All transition metals need to be defined by the charge associated with their anion. Bromine is a -1, and there are 3 of them because the subscript tells us there are 3. So 3 minus 1 charges is a minus 3 charge. We have 1 iron to balance that, so iron must be 3 plus. So when we name this, we say the name of the transition metal, iron, in lowercase letters, right? And then the Roman numeral 3 to represent the charge, and then bromide. And once we've named the charge on the metal, we don't have to say anything about the bromide because it's defined as 1 already, and that's what gave us the 3. So iron 3 bromide. Let's look at letter C, right? Number C. There you go. This is why I get the big bucks. Okay, cuprous bromide. So cuprous and cuprit, right? 2 different endings, right? The us ending is always the lower charge, and copper is usually 1 or 2. So this is going to be copper 1. So if we were just writing the systematic name, we'd write copper 1 bromide. The formula is Cu plus bromine, which we found out from the last problem, is 1 minus. So it would just be CuBr. And then finally, problem D here, manganese is going to be defined by the anion as well because it's a, bear with me now, transition metal, right? It's a transition metal, which means the charge on the transition metal is defined by the anion it's attached to. There are 3 oxygens. Oxygen is a 2 minus, so O2 minus, O2 minus, O2 minus, which gives us a total of minus 6. Right? So to charge balance that, we need a positive charge of plus 6, right? The 6 plus minus 6 is 0, and that our compounds are charge neutral, which means we have to distribute. There are 2 MNs, right? According to that subscript. So Mn, we have to divide that charge by 2, so that gives us Mn 3 plus, right? Is 3 plus 3 plus is 6 plus. And so that works out. So we have Mn 3 plus, and so we would write that name as, oops, let's go, manganese 1, 2, 3 oxide. And since it's already defined as minus 2, that means we have to have 3 oxides to go with these manganese 3 plus, and we'd have 2 of those. So Mn2O3 is manganese 3 oxide. Thank you for paying attention. Have a good one. All right, let's look at problem 20 or 2.90 from the homework. Starting with A, we have CO, which is the transition metal cobalt. And again, whenever you're naming something with a transition metal, you must get the charge from what the metal is attached to. In this case, it's attached to oxygen, so this is cobalt 2 oxide. Again, oxide's a 2 minus. There's 1 cobalt, so we must have that be 2 plus. End of story. Mercury 1 chloride. Mercury is Hg, in case you didn't know. And chlorine, of course, is a minus 1, so plus 1, minus 1, that's charge balance. Mercury 1 chloride. This next one requires us to know a few things, right? So this first part is a polyatomic anion here, which is an acetate. And acetate is a minus 1 anion. There are 3 of them. And this Pb is then lead. So lead 1, 2, 3 acetate. Okay, well, we'd be done there except for this dot 3H2O. What does that mean? Well, whenever we have a dot 3H2O, it's what we call a hydrate. So this is heptahydrate, right? Not hepta, it's 3. What's that? So we have 3 trihydrate, and it just adds on. And the water, the 3H2O, is part of the molar mass of the compound. So this is lead 3 acetate trihydrate. All right, and finally, chromic acid. There's another one of those ic us. So for chromium, the ic stands for Cr3 plus, and oxide is 2 minus. Right? So we need 2 chromiums, Cr. Let's just cross that out. Cr2O3, because you need 2 of these and 3 of those to make the +6 charge and -6 charge. Now, if you've been watching, this makes sense. If you haven't, then you need to go back and review maybe one of the other videos. All right. Thank you. All right, let's look at the second part of this problem, figuring out the molar mass. Now, when we calculate molar mass, we have to account for all the elements in the formula, how many times they occur, and add them all together to get an entire total amount for the compound. Now, remember, when we talk about the molar mass, we're talking about a mole of atoms or grams, right? So for nitrogen, that would be 14.007 grams, hydrogen 1.0078 grams, sulfur 32.06 grams, and oxygen 15.999 grams. Now, that would be great if we were only looking at one of each, but in this case, we have 2 nitrogens, so we have to multiply that by 2 because NH4 twice gives us 2 nitrogens. Remember, we distribute this subscript through everything in the parents. So hydrogen, there's 4 inside the parents, but we do that twice, so times 8. And then sulfur, just 1. And then oxygen has 4. So once we get the total for this, we'll know the entire molar mass. All right, so let's say we did that. We took 14 times 2, 1 times 8, 32.06 times 1, 15.999 times 4. That would give us 28.04 grams of the molar mass due to nitrogen, 8.0624 grams due to hydrogen, 32.06 grams due to sulfur, 63.996 grams due to oxygen. Gives us a total of 168.114 grams for the molar mass, and that would be grams per mole, molar mass. But remember, when we're doing significant figures, we can only go by the least number past the decimal. So that would be here. So our total would be 168.11 grams per mole ammonium sulfate, NH4 2SO4. All right, thank you. All right, let's look at problem 2.124, the NXOY, nitrogen oxide. So the X stands for how many nitrogens there are, and the Y for how many oxygens there are in any particular nitrogen oxide. So let's look at 46.69% nitrogen. What that means is that 53.31% is oxygen. What we also know is molar ratios are going to be whole numbers. So let's look into how we would determine the molar ratio based on these percentages. Well, what we can do is we can say out of 100 grams, 46.69 grams are nitrogen. And in order to get the number of moles, we just divide that by 14.007 grams of nitrogen per mole. And then we can also do the same for oxygen. And that will give us a molar ratio, I'm hoping. Grams O divided by 15.999 grams O. And let's see what that gives us, shall we? So doing the calculations, 46.69 grams of nitrogen divided by the molar mass of nitrogen, which is 14.007 grams of nitrogen, so we get 3.33 moles of nitrogen. When we do the same thing for oxygen, the 53.31 grams of oxygen present in our compound divided by 15.999 grams of oxygen, we get a molar ratio of 3.33 moles of oxygen. So taking the smallest one, which is either 1, we get a 1-to-1 ratio. So our ratio for this compound is 1 mole of nitrogen for 1 mole of oxygen. We would call this compound nitrogen monoxide. All right, thanks for your attention. All righty then, here we are. Let's look at 2.124, part 2, where the nitrogen content of a nitrogen oxide molecule is 36.85% nitrogen. Again, we can use the ratio of 100 grams to find out that we have 36.85 grams of nitrogen in this compound and 63.15 grams of oxygen in this compound. We can then convert to moles, 36.85 grams of nitrogen divided by 14.07007 grams of nitrogen and 63.15 grams of oxygen, converting to moles of oxygen by dividing by 15.997. So let's do that. All right, then we do the calculations and we get 2.6308 moles of N and 3.947 moles of O, What we're going to do is we're going to take the smallest number of moles and divide it into itself, which gives us 1 mole of N, and we're going to do a 2.6308 dividing by 0.26308 into 3.947, and that gives us 1.5. So if we double that ratio, we get a whole number ratio. And so that would be 2 moles. Let's just slide this over a little bit. 2 moles of N, N2, and 3 moles of O, N2O3. So this is dinitrogen trioxide. Okay, have a great day. Oh, let's be a little clear. Why did I multiply both by 2? Well, because I had a 1 to 1.5 ratio, and we need a whole number ratio in order to have a compound, correct? So if we multiply both by 2, I get 2 nitrogens and 3 oxygens. Okay, thank you. To go from grams to moles already, which is just taking the gram amount we're given and then calculating the molar mass of the compound we're interested in. And then to go to molecules, all we do is multiply the ratio 6.022 times 10 to the 23rd molecules per mole. So we'll start with our grams, 2.010. Start off just right. 2.010 times 10 to the 2 grams. And then we have to calculate the molar mass of sucrose, right? Which is C12. So 12 times 12.01 grams. And then H22. So 22 times 1.0078 grams.
And then finally, O11, which is 11 times 15.999 grams. And that's grams of carbon, grams of hydrogen, grams of oxygen. And just add those all up. And I'm doing it again, recording you. Awesome. All right. Dr. Houlis, all these videos have the same girl in them. Oh, well.
It's a little creepy, huh?
Yeah, kind of. I don't know on whose part, though.
I don't know. This
Like,
girl's
well,
so confused in all 12 videos.
this is what makes it real, right? Okay. So, did you get a number for me while we were chit-chatting?
Oh, no. Hold on. 175.98. Okay, I got 342.2806.
Sounds good to me.
Okay.
342.
2806.
28. Okay. 342.06. Okay. Grams. And then, so we're going to use that up here. And we're going to say 1 mole C12 H22 O11 is 342.2806 grams C12 H22 O11. You notice I'm always, what am I always doing? Labeling, right?
Yeah.
Always labeling. Okay. And now the step that we haven't done before is to go to molecules. And it turns out 1 mole of C12H22O11 equals 6.022 times 10 to the 23rd molecules of C12H22O11. So we just do that. We want to get rid of moles, so mole on the bottom. C12H22O11 and 6.022 times 10 to the 23rd molecules. And is that going to fit? It will. C12H22O11. Yeah. And what's going to happen there is you have to put that in your calculator properly. And what I always suggest doing with that is putting brackets around anything that's a power of 10, and then dividing, and then when you multiply, put 6.022 times 10 to the 23rd in brackets again. If that makes sense.
Do you mean like each one of these in brackets, like each thing, or do you recommend just doing each one and then figuring it out? And then...
No, like each one in brackets, just put brackets around 2.010 times 10 to the second, and then divide by 342.2806, and then multiply with brackets 6.022 times 10 to the 23rd.
Okay. And now that number, the 6.02 times 10 to the 23rd, you're saying that 1 mole of, what is this, sucrose?
Yeah.
Is equal to that. Is 1 mole of anything Avogadro's number?
Yeah.
Okay.
Right. In molecules, right?
Okay.
Right. Okay. So that's that carryover. So really you could say that 342.2806 grams is 6.022 times 10 to the 23rd molecules without having this step. But I like to have this step in here because we go from grams to moles, but That way we know when to include molecules, because to get to molecules, you have to go from grams to moles, but you don't necessarily want to just go from grams to molecules, right?
Right.
So.
Okay. And where did that number? Oh, never mind. I'm gonna ask a silly question. Got it. Okay. Let me try to put it in and see if it sounds funky. Okay. Divided by 280. Times 6.022 times 10 to the 23rd.
Correct.
Equals whoa. Three 3.536344157 times 10 to the 23rd.
That sounds about right.
Really?
Right, because if you look at, we have about 200 grams, right? Which is less than 342 grams. So our number should be less than 1 mole. So that's good. So you said it was 3. Let's just go with 4 digits.
Oh, okay. Then it's 3.54. No, 3.536. We're going with 4.
Okay. 3.536 times 10 to the 23rd?
Yeah.
Molecules. C12H22O 11. Good. Good one.
22L11. Okay, now number 12. Okay.
The law of constant composition says that things are always in the same ratio when they're in the same compound. And so what happens is we make something in lab. Let's say we make this compound, and it contains aluminum, carbon, and hydrogen. And we send it off for analysis. And when it comes back, it gives us these percentages of what each substance is or what each element is. So, and this is a little bit more difficult than normal, but we can do it anyway. So what happens is these percentages are given to us, and we can base the empirical formula, which is the smallest whole number ratio of elements in the compound, to the elemental analysis. So in this one, right, we're going to have a 0.24, boy, we are really starting downfield too, gram sample, and it contains aluminum, carbon, and hydrogen, okay? And is combusted, which means we burn it in the presence of oxygen. And so it gives 0.5671 grams of carbon dioxide, right? And then 0.2902 grams H2O.
You mean when you say it gives, you mean it's losing that?
I'm sorry?
When you're saying it gives, are you meaning that?
Right. So when you burn it, it yields or gives, it makes. Those are all interchangeable terms that chemists use. Okay, so keep all your significant figures in this, since the formula is not a simple one. Great. So I expect very few people to get this problem correct, right? But the points are based on how much of it you do properly. So if we're given this much and we have this residual aluminum oxide, which is fine because we're not measuring oxygen, so that's kind of a it doesn't really matter because the aluminum's going to be whatever's left over. But what you have to recognize is this compound is made of carbon, and we have grams of CO2, right? So what we want to do first is we have to convert 0.5671 grams of CO2 to moles of CO2. And that's 12.01 plus 32. So that's like 44.01, I believe, grams of CO2. And then we need to find how much carbon's in there. So the ratio, fortunately for us, is 1 mole carbon per 1 mole CO2. And what that'll do, and then 12.01 grams of carbon is 1 mole of carbon. And that'll give us the grams of this part of the sample that is carbon. Are you with me?
Okay. Where did you get the 4.01? You just did the
Yeah, 12.01 plus 15.99
times 2.
15.99.
I got you. Okay. I was just trying to make sure I'm following that. And then you're going to moles to grams.
Right.
Okay.
So, and why am I doing that? Okay, because this compound is composed of carbon, not carbon dioxide, right? So we burned it and we captured this much carbon, right?
Okay.
And that's so that we have to find out what that is. And so we'll do that math. Yeah, this is you need a lot more than what I'm giving you right now, but bear with me.
Great.
We'll get through the problem, and then when it's introduced, it'll make more sense. Which will be probably Tuesday now. 0.5671 divided by 44. 1 times 12.
You get 0.1547575.
I did. So 0.154757. That's plenty. Grams. And then, so the other component that we need to find out then is the hydrogen.
Okay.
And so we're going to do the same thing. We're going to take the 2.2902 grams of H2O. And then we're going to convert that to moles, H2O.
Are you only concerned about the carbon and the hydrogen because there is no oxygen in the top?
Correct. Okay. Right. The oxygen came from burning this compound.
Okay. Okay. Where are you getting? Oh. Okay, so.
So then there are 2 hydrogen atoms, right, in H2O. So 2 moles of H per 1 mole of H2O.
Oh.
But then remember, when we're doing moles, we only do the gram amount, 1.0078 grams H per 1 mole of H.
Why did that change there? Why is there 2 in the moles but not in the grams?
Right, because remember, this is the molar ratio, and a mole is always just the amount of H or whatever you're looking at, carbon. Even if the molar ratio is 2:1, 1 mole of carbon atoms is always 12 grams. 1 mole of hydrogen atoms is always 1.0078.
Okay. I'm not sure I believe you, but I'll go with it.
Okay. I mean, there are you could do it with 2. If you put a 2 here, this 2 would cancel, but this would be twice as big. But in order to avoid confusion, I always simplify it. Like, I don't like to skip steps, because in a long process of 21 points, you miss one step and I can't see where you missed it, then I can't give you points. And that's what I'm here to do, is give you points.
I got you. Okay. Wait. Oh, you figured out that 18.01 number?
Right, is the molar mass of water.
Okay.
I think we did that one yesterday as well.
Okay, I got 0.032477907.
That's what I calculated as well. 77907 grams. And that's hydrogen. This is grams carbon. So if we know how much carbon there was, and we know how much hydrogen there was, we also know how much aluminum there is.
Right.
By adding these 2 together and subtracting it from the original.
I'm following.
You are following?
Yes.
Nice. Okay. So what do we have?
Oh, do you want me to actually do that?
Okay.
I got distracted. My electrician just showed up.
Oh, you need to get back to work?
I don't think he needs me.
Oh, okay.
I wish he did, though. He's very attractive.
Another one? What? We just collecting attractive guys now?
Let's have a whole list of them.
That's not me saying this, by the way. That's you.
No, I know.
Yeah, I know, and we're recording, you know.
Oh shit!
Not like we're a morning show.
Hey, is that a 4? Oh, that's a 4. Okay, 0.2452 minus 0.154757. 779 equals 0.0579651. Did you get that?
I did not do it, so go ahead and give me the answer.
0.0579651.
Okay, so we have lots of significant figures there. They're not really significant, but we can use them. So the next step in this process is to convert each one into their moles. And so this is the amount of each one, and now we divide by their moles to get a number. And so we would take, I guess we're going to have to start over on another board. We'll take our amounts. We'll get rid of this. Get rid of this. Okay.
Although I think that the aluminum amount is written down wrong. 0.5799651. So just put it. We just added a 4 for fun.
For fun. Okay. Just to change the problem.
Just make it interesting.
Okay, so So step one is to find the gram amount, and we did that. And so now we're going to convert. Step two is to convert to moles. So 154,757 grams of carbon divided by 12.01 grams of carbon.
Well,
And then
okay, so you're taking the amount and you're dividing it by one of their one mole.
yeah,
Okay. Why?
because the molar ratio gives us the whole number ratio of aluminum to carbon to hydrogen in the compound. And so there's a couple of steps, and this is the first step. So 1.0078.
So always, if you find out how much of something is in a solution, you can divide it by the total amount of it. You can divide it by its molar number and get what?
Right, we'll get the ratio. So we had this thing analyzed, and it came up with these amounts. And because we don't know what those we could just take the percentages and do it that way. But because we actually have the gram amounts, we're going to find the molar ratio. And it's not solutions, it's compounds, right? This is for solids. Solutions has a whole different way of characterizing those amounts.
Got it.
Okay, so finally the last one is 0.579651 grams of aluminum. And aluminum is 26.981.
Okay.
All right. And I will do these with you this time.
If you do the aluminum, I already did the carbon. I'll do
okay. 0.057. Oh.
4.779 divided by oh boy, that's a big number. 1.8033259. Hi. I did. I see that he's here. Does he need me? Oh, okay. Sounds good. Okay. Thank you. Bye. Okay. I do need to go meet with my electrician in 1 minute.
Okay.
Okay. So I got for carbon, I got 0.012885678.
Okay.
And for hydrogen, I got 0.018033259.
Okay, I completely missed that one. 0.01.
8033259.
Okay, so this is the number of moles, and what we do then is we divide the smallest one into each of them. So the smallest one here would be the carbon, I believe, 0.12. Yeah.
Okay.
And so you divide carbon by 0.128856778, and then this one by 0.012885678, and then this one by 0.012885678.
And you're dividing by the smallest one.
Smallest number of moles.
Okay.
And that gives us the ratio between all three. And we should probably stop right there so you can go take care of your stuff.
Okay.
And that doesn't finish the problem, but it gets us almost to the end.
Okay.
All right.
Okay. That wasn't that confusing. I like that more than the other.
It's kind of fun. This part's kind of fun.
Yes. Thank you for your help. Sorry.
No worries.